Welcome to this HydroCAD video on the new features added in HydroCAD 10.1. This will be a quick overview of what's been added in this new release in early 2020, and you can get additional details on specific features in the separate videos devoted to each topic. The first thing I want to discuss are capabilities in HydroCAD for adjusting the rainfall duration, and you will find a separate dedicated page on the website that discusses this issue. HydroCAD has always provided the capability to change the storm duration, that is to rescale a storm such as from 24 hours to 12 hours or some other duration. But this procedure works by compressing the storm or rescaling it to that duration. What we've now added in HydroCAD 10 is the ability to also trim a rainfall to a different duration. And this is very helpful when you want to extract a smaller storm basically from a longer one. So in this illustration, the bottom illustration shows the traditional operation of HydroCAD when you choose to rescale a storm, that it would take, for example, the entire 24 hours and compress it down to 12. The result of this is that the middle of the storm, the peak intensity, is doubled as you do that. So this is not necessarily what you want to do with most distributions. This rescaling is appropriate for Huff distributions, but that's one of the very few rainfalls that's intended specifically to be rescaled by this procedure. So what we've added in HydroCAD 10.1 is the ability to also trim a rainfall distribution. And this would allow you to take, for example, a 24-hour storm and extract the middle 12 hours out of that storm. So you're producing a shorter duration storm which correctly preserves the intensity characteristics of that curve, but only contains the 12-hour depth as opposed to the full 24 hours. And these capabilities are visible in HydroCAD when you view the settings calculation screen on the rainfall tab. Normally, each storm you choose will come up with a default duration. If you want to change that duration, then we could set this to trim, for example, and we could trim that 24-hour duration down to 12. Or if we really wanted to, we could use the scale option. Now, if we do try to rescale it, we will get a warning indicating that this particular storm should not be rescaled. You could rescale it if you insist, but in general, the better procedure is to trim those storms. So looking at this sample project, which I pulled up, I've already got rainfall events defined for the regular 24-hour storm, and then a 12-hour scaled version and a 12-hour trimmed version. So here is the initial 24-hour distribution showing a peak intensity of 3.21 CFS. And if we go to the Events tab and update this for all the events, we can see how these compare. So for the regular 24-hour duration, we have a runoff peak of 3.21 CFS. If we rescale that to compress it down to 12 hours, that goes up to 4.12. And if we trim it, we get an intermediate value of 3.82. So just to be aware that this capability is there if you should need to rescale a distribution. In general, you will want to use the trim option as opposed to the rescale. Projects coming in from earlier versions of HydroCAD, if they've been rescaled, they will continue to be rescaled and produce exactly the same result. So this capability is an option that you can use on HydroCAD 10.1 and later. The next capability I want to look at is the specification of the unit hydrograph. Going again back into the settings calculation screen on the unit hydrograph tab, this is where you would normally select the unit hydrograph to be used for a specific project. With HydroCAD 10.1, you also have the ability to specify a different unit hydrograph for each subcatchment. So if you happen to have a site that was characterized by very different terrain, such that a different unit hydrograph was appropriate for some portions of that watershed, then you could enable this option to allow each subcatchment to use a different unit hydrograph. And then we have two subcatchments here demonstrating that capability. The first subcatchment is using the standard SCS unit hydrograph, and the second one has been adjusted to use the Delmarva unit hydrograph. And so you can see there's a considerable difference in the peak runoff based on the different unit hydrographs that are in play. And that node-specific unit hydrograph is set by editing the subcatchment, and you will see a new unit hydrograph tab, which appears as soon as you've enabled this feature in calculation settings. And you can specify that, yes, this specific subcatchment will use a different unit hydrograph, and you can pick the unit hydrograph that is to be used. So, very simple setup, gives you that capability to handle differing unit hydrographs within the same project. It's not used very often, but this avoids the need to have to break that project up into several HydroCAD project files and then link them together. Now you can do it all combined together into the single project file. The next feature I want to look at is the ability to have a sloped grate or orifice. In this pond that we already have set up, if we edit and go into the Outlets tab, I already have an orifice grate device set up. And the first thing you'll notice on the screen is the illustration that appears on the right-hand side. And this is very handy when you're setting up an orifice array, which is commonly used to model a grate. You have a number of rows and columns of openings. And so you can now see a visual layout of the grate that you're defining. It just helps you make sure you've got the parameters correct. You'll notice it shows the percentage of open area in the grate, which is another parameter that you can use as a cross-check to make sure you've set things up properly. In this particular example, we've specified the overall grate dimensions as 24 inches square, and then the openings are uniformly spaced within that. And we can change the number of rows, and you see as we get too many, it's pretty clear that they're overlapping. We get a visual indication here of whether or not the layout is appropriate. So we can make adjustments, we could increase the size of the openings, whatever you need to do. We also can deselect the grate dimensions, and we get just the openings now. The software is no longer looking at the flow around the grate perimeter. And in this instance, it doesn't actually matter what the spacing between the openings is, but it's still showing us the relative size of the openings and the array, the number of columns and rows that we're using. If we wanted to change the orientation of this grate, the default is that the grate is in a horizontal plane, like a grate sitting in the middle of a street. We've also had the ability to switch that to a grate in a vertical plane. And when we do that, it also needs to know the spacing in between the rows in order to display them reasonably, because of course each row is at a different elevation. And we now have a new option to set a custom angle. So we can specify the angle in this box. So we could set this at 30 degrees. So now we have a grate which is inclined at 30 degrees from horizontal. The parameters are set much the same as if it were in a vertical plane. We still need the size of each opening, number of rows and columns, and the spacing. So this gives you broader capabilities for modeling a grate and makes it much faster to verify that you've actually set the correct parameters by using the illustration that appears when you enter the grate. The next change we have pertaining to ponds is the ability to have a delayed outlet device. Essentially, this would be a computer-controlled outlet of some type. It could be a gate or a rotating weir. There's various options. But the key is that this is a device which will open at some point in the storm. There will be a trigger, either time and or elevation, that will cause the device to start opening. And we have an example here of actually a rotary weir. If I double click this in order to open the report, here we have an inflow and an outflow hydrograph. And it's an interesting curve that appears here. At first it appears that there might be oscillations in this, but if you zoom in, this is actually the correct behavior for a rotary weir that's opening at given increments. Depends on the specific device, but the device may be set up so that it only moves in a 1/4 inch increment or something of that nature. And that's the kind of behavior that we're getting here. If we go in and edit this pond, look at the outlets, look at our rotary weir. This is where all the configuration is set up for the more general scenario of a delayed outlet device. So this could be a rotary weir, as we have in this case, or if we uncheck that box, then it represents a gate valve, essentially, that's opening. And we specify the vertical operating range of the device, the elevation for the bottom of the opening, the step over which it's opening. So if this device is opening just progressively at a certain time increment, then we'd set the step here. And then we have the trigger points. We have the water surface elevation that has to be attained for the device to start its activation process. Then there's a time delay, how long after we hit the trigger before it starts operating, and then the exact amount of time it takes to transition from its closed to its fully open position. And then far right of this screen, we are able to set the inlet size on this device. So this might be the top of a rotating weir. It might be a gate valve. It depends on exactly what you're modeling. If we press the help button on the screen, as with all the data entry screens, you'll get complete information on the outlet device. And scrolling down here, if you click on the topic for rotary weir, you get a illustrated screen that shows you the setup of the weir and the exact geometry that's being modeled as that weir opens. The next item I want to discuss is the channel outlet capability on a pond. So scrolling over here on our sample file that I'm working with, a very common situation, or fairly common with pond outlets, is that you may have a pond that simply outlets into a channel. It might not have specifically an orifice or a weir or culvert or other discrete control device at that point, but it might just enter into a channel such that the discharge is going to be governed by normal Manning's flow within the channel. Previously, if you wanted to model this kind of a device, you would set up a reach representing the channel, use that to produce a stage discharge curve right here, and then you could take that stage discharge curve and you could re-enter that into the pond as a custom outlet device. So you would re-enter the rating curve there. That process is made considerably easier by the channel outlet capability. So when we're editing this pond on outlets, we've got two outlets at the moment. I've got a culvert discharging to primary, so that's a lower discharge from the pond, and then we perhaps have an overflow point a foot higher where we hit a channel outlet. For the channel outlet screen, it's very, very simple to set up. All you're defining right here within the pond is specifying where that flow is going. And in this case, we do want to separate out the flow, so we're routing it to secondary, whereas our culvert that's already configured is going to primary, so it'll separate these two flows. The invert elevation is grayed out here because that data is being pulled back from the channel, the reach that we're routing into. A discharge multiplier could be set if you had more than one of these side by side, or for some reason wanted to adjust the flow up or down, then you could use the discharge multiplier. So if we OK this a couple of times, and then I'll double click the pond in order to open up a report. And so now our secondary outflow here in red is the discharge that is going into the reach. And to show you how this really works, I've got a wider version of the channel, which is connected now, and a narrower version. So if I take the outflow and I drag it over to the narrower channel, if you watch this peak at 2.49 CFS, when we go to the narrower channel, it has less flow capacity at the same elevation, and the flow drops down to 181. So this is demonstrating how it's dynamically taking that rating curve and pulling it back into the pond. You can also see the actual rating curve if you go to the stage discharge curve for the pond and flip to the 2D view here. This portion of the curve in red is that channel outlet opening up the reach and going to the discharge curve. That's this curve here. The scaling is slightly different, but you'll notice we're going from 0 to 3.2 CFS on each of the scales, and the depth is going from 51 elevation up to 52 foot elevation, which is this 0 to 1 foot increase. So very handy capability, and it supports any kind of reach geometry that you might want to use. So you can use any of these options to define your reach. They all then produce a rating curve which is pulled back into the pond. So the result of this is that the pond discharge will be regulated by that rating curve, and then you will also get the reach routing, which will occur by the hydrograph going through the downstream reach. Also in the general category of pond outlet devices, there is a new automatic overflow capability. And this is handy if you have a pond or some volume which fills with water, and when the water gets to the top, you want it to just spill over. Previously, in order to handle that, in order to model it, you would need to set up a weir or perhaps a horizontal orifice at the top of the storage volume in order to model the overflow. You would also need to define the storage or the temporary storage that's slightly above that spillway elevation. That's actual temporary storage where the water is sitting before it flows over that outlet device. So you'd have to set up each of those items in order to get an accurate routing. With the automatic overflow capability, we have a simplified procedure that gives you the approximate overflow behavior. The only thing you have to do to use this feature is just come over to the Advanced tab, and under Automatic Overflow, you would just select the routing that's to be used for the overflow. And so this will cause any excess as the pond fills above its defined storage to go through the secondary. So if I were to come in here and set this to none to turn off the automatic overflow, now we're attempting to push the entire flow through our outlet devices or our one culvert outlet, and we are in fact exceeding our storage range. We're pressurizing this pond, but what we really want to happen is just for the water to overflow. So this is a simple but effective mechanism where we can just go in and set up the automatic overflow to go to secondary, click OK, and we've updated the model. If you want a really accurate number, a more accurate number as to what the overflow will look like, then you should set up the actual overflow device, whatever it may be, and also define the temporary storage above that crest or spillway, because that temporary storage is contributing to the peak attenuation capabilities of the pond. The water is being detained there, however briefly, whereas when we use the automatic overflow, the water never comes above the top of the defined storage. It's just thrown out to this overflow discharge point immediately without any additional delay or volume-based attenuation. A related feature that we've added is the automatic overflow on a reach. In this example, we have a reach where we're exceeding the capacity of the reach. You notice we have a warning message indicating we've actually overfilled the reach, but there's no information in the model to indicate how to handle the excess, so the water's just stacking up, getting unreasonably high, essentially above the banks. We now have the capability on the Reach Advanced tab to divert that overflow. So if the channel or reach fills above its bank full condition, the additional volume will be discharged as a secondary outflow, which is what you can see here in red. So now we've essentially split that flow into two pieces. We've got the portion going through the reach channel itself and arriving at the downstream end, but we also have another portion in red which is overflowing, and we obviously should route that somewhere else in the model, and obviously we have two outflow handles indicating the primary and the secondary outflow, which are now available for routing. Next up, we have a couple of capabilities that have been added to a link, and these are allowing us to basically take a slice off the inflow hydrograph, and we can slice by volume as shown here where the first acre foot is being sliced off, or we can slice by time. And this was added in order to simulate systems that might have automated gating that's allowing a specific volume of water into a point in the system, perhaps for treatment, or gates that are operating on a time sequence that allows the flow only between a certain 2 points in time, before a point or after a point. All of those scenarios can be handled. If we look at this example for the first acre foot and open up the hydrograph, what you see here is that in blue we're getting the first 1 acre foot which is coming out of the pond. out of the link. If we switch this to the 2D view, you can see the curve in blue, which then drops to 0. It's hard to see here. Let me turn off the secondary outflow, make it a little easier. So now you can see the outflow curve, and I'll turn off the inflow as well. So there is the primary outflow, which is 1 acre-foot. If we switch over here to the link summary and look at the report, you can see that we've got a total of 1.3 acre-feet coming in and exactly 1 acre-foot that's coming out of the primary. The remaining flow is going to secondary, and the two of those add up to the total inflow volume, as you would expect them to. Again, if we come back and turn our curves on and look at secondary, the secondary here picks up exactly when the primary drops off. So we can use this to shave off any volume of water we need to at the beginning of the hydrograph. And we can stack links in sequence if we want to break the inflow into several different slices. We're not limited to just a single slice, as shown in this example. A similar capability allows you to do a time slice. So now, rather than specifying the volume that's to be sliced off, we're specifying starting and ending times. So flipping to 2D view, and if I zoom in here a bit, and let me turn off some of the additional curves to make this a little bit easier to see. So let's remove the inflow, and let's remove the secondary. And so now what we're looking at is just the flow between 14 and 16 hours, which is what we've specified within that link. If we edit the link and go to the Advanced tab, you can see here we have the starting time and the ending time. And that's what's used in order to define a time slice. It's very similar capability, which is used to do the volume slice. You just come down to a separate box and you specify the volume, which is to be sliced off at the beginning of the hydrograph. So this expands the capabilities of a link. A link is sort of a generalized computational tool that can be used to simulate very specialized behaviors. Often they may be automated systems that are switching or controlling it at some specific point. So it's not strictly dependent upon the flow in the system or the volume of water in a pond. It allows it to respond to other inputs and triggers. Next, I want to talk about some of the new reporting capabilities added in HydroCAD 10.1. And to do this, I'm going to pull up the Mountain View Housing Complex project, which is pre-installed with HydroCAD. And within this file, if we go into Calculation Settings, Rainfall, we could then click View All in order to see a table that shows us all of the rainfall events that have been defined for this particular project. That's a little indirect in order to get in there if you just want to view the rainfall settings. So you can now open the project report window, and there's a new tab here on the left labeled Rainfall Events. And this gives us a complete listing of all of the rainfall events that have been defined for this particular project. This mode column is used to indicate the mode for either trimming or rescaling a rainfall distribution. So if the duration were adjusted from its default value, the particular method would be indicated in the mode column. B to B is the number of back-to-back storms. This is, of course, the total rainfall depth, and then the antecedent moisture condition or antecedent rainfall condition are shown in this final column. There's also been an enhancement to reporting when you run a multi-page report. So if we go to Print Report, we have a new option here to list the events within the beginning of the report. So right up front, it'll give us a listing of what our event definitions are for this project. There's also an option that's been added for a table of contents, which will automatically generate just that. At the very end of your report, it gives you a list of everything that was included in the report with a page number referencing where that item appears. We also have a capability, which is very handy, to do multi-event tables. And a multi-event table, in addition to the normal report which is run for each event, this will accumulate all of that information in a single table for each node. And that table will give us a summary of what the results are for each of the events, quite obviously. So let's just select one pond in order to simplify this report. and then do print report, and we'll run it for all the selected events, but for just the one selected node. And we want to include the list of events, we want the multi-event tables, we want the table of contents. Good. So we click print, and in this instance, let's run this out to a PDF file, which is basically the way to proof or preview any of your reports. Okay, and so now we have the PDF, and the first page has got the listing of rainfall events, just as we've defined them, and this is the same report that you can see on the project's report screen. And then we've got all of the reports that were selected for this particular pond, and this first set is for the 2-year storm, and of course this report will go through and show us the 2, the 5, all of the storms that have been selected. We get the complete analysis, 25, 50, and 100, and then we get to the very end of the report, and we're going to have the multi-event table. So here we can see each of the events, inflow, outflow, discharge, elevation, and storage for each event for that particular node. So one of these tables would be produced for each node, showing a summary of all the multi-event information. And now the final item in our summary of new features in 10.1 is the undo command. The undo command is used primarily to record and reverse changes that you've made to individual nodes within the project. This can include moving a node around, rerouting it, drag the outflow to a different place. You might renumber a node, change that to 44. So these are simple visual things you can see on the diagram. We can create new nodes. We can delete a node. And all of these things get recorded in the undo history. When you want to undo something, you can use the key that's common to many programs, simply Control-Z. And Control-Z will bring up a complete undo history. And this is a list of all of the changes that we've made. You can see moving a node, rerouting, renumbering, moving, deleting, and it shows you the node involved. And then each of these is available to be undone. And if we choose an item in the list and then click undo, so there's a node reroute of subcatchment 3S. So if we do an undo here, and we get a prompt to confirm that we really want to do that, and we can suppress that message if we don't want to see it again. We click OK, and the routing was reverted to where it previously was. Every time we undo an action, it also generates a corresponding redo item on the top of the list. So we could go to the redo item and redo that, and it would restore the most recent routing that we'd set up for the node. So we can do this in the undo history. It allows us to do things out of order. We're not limited to just undoing things from most recent backwards. This history will be set up to show all of the nodes in the project, or you can set it up to just show individual selected nodes. And so let me cancel that and come back here. So if we select just this node, for example, and then do a Control-Z, we now have one selected node, and it's showing us only the undo actions for that node. Or we could toggle it to show the undo actions available for all of the nodes within the project. Either way you prefer to do it. We can undo things immediately by pressing Control-Alt-Z if we don't want to have to go back through the undo history. So if I press Control-Alt-Z, you can see we have a routing change here. Press again. The node I deleted comes back. Press again. That new node goes away, etc. back through the process, and here the node got renumbered. So we can use either approach to make changes. The other primary use for the undo command naturally is when you're editing a node. So if we were to come into this node, let me open up a report window, and at the moment we have an area of 12 acres here. So let's say we want to change that area, increase it by 4 acres or so, and click OK. Now our area has gone up to 15.6. Now, if we decided, oh, we want to set that back, then we have the capability to press Control-Z. There's our undo history, the subcatchment, 4S, and you notice the activity is a node edit. We can click undo, and that reverts right back to where it was before. So any editing changes you make to the node, rerouting, changing position, all of those most commonly used capabilities are recorded in the undo history and can be reversed whenever you need to. So that's a summary of new features added in HydroCAD 10.1, and again, you can find more details on individual features within the specific topic dedicated to that area of HydroCAD. Thank you and have a great day.